You only have two choices, right? The waves could bounce through each other. They could also pass through. So the way to tell is if you have two waves that are totally different sizes, then it's obvious. If the big wave bounces back, then we know that waves bounce back. If the big wave passes through, right, then it passes through. And obviously, yeah, big wave's not going to be stopped by a little wave, right? It's going to keep going. Oh, my computer's working hard there. Ah! So it's going to pass through. You think about it in real life, it makes sense. When you're talking to your friends during lunch, it's not like you can't hear them and they can't hear you. Your sound waves pass through each other. So on this little worksheet, what we're trying to do is not let the computer animate how the waves work, but we're going to try to understand it ourselves. Anyone a big fan of action movies? You know, like all the superhero ones they have now? It's awesome, right? And one reason why action movies are so cool is the computer's effects are so realistic. And one way we can make them realistic is we can animate waves like water, explosions, and fire accurately. So all it is we're trying to model what happens in real life. So here we have two waves. We have wave A and wave B. Let's say we're at the Hinsdale Central wave pool again. And what we're going to try to draw is what happens for the first 4 seconds. And to make it easier, I'm going to use different colors. You can pick any colors as long as you're consistent. I'm going to call wave A red and wave B blue. And what we want to figure out is each wave moves at 2 squares per second. Let's say it's 2 feet per second. So after 1 second, if wave A was here, what's it going to do? It's going to move over what? Like 2 more feet, right? So it's going to move over 2 squares. So if the wave was here, wave A is going to actually move over 2 squares. It's going to be here. So in other words, instead of being there, I'm going to draw it over here, 2 squares. And notice the wave is 2 feet tall by how many feet wide? 1, 2, 3, 4, right? Like that. That's wave A. Make sense? We're just drawing a wave moving, yeah? I'm trying to be like a cartoonist, except these are really lame cartoons. Got it? How about after 2 seconds? What would wave A do? It would move over another what? Another 2 feet. So instead of being there, it's going to be here. And again, wave A is 2 feet tall by how many feet wide? 1, 2, 3, 1, 2, 3, 4. This isn't hard to do. You just can't be googly-eyed. There we go. After 3 seconds, if the wave travels at 2 feet per second, actually it would be really awesome to have a Hinsdale Central wave pool. Over here, there we go. You guys see what's going on? This is not rocket science. 1, 2, 3, 4. All we're trying to do is draw what happens to the wave every 2 seconds. And if it moves 2 feet per second, all you got to do is shift the wave over what? By a factor of 1, 2, 3, 4. By a factor of 2. 1, 2, 3, 4. There we go. Like that. Wow, so exciting. Now we got to do wave B. Now we're going to go back and draw wave B. And what I found is, if you try to do this all at once, you get confused. But if you just do one part at a time, it really makes sense. It's a lot easier. So now let's do wave B. So here we got wave B. What's different about wave B? Instead of being a positive 2 crest, it's a negative what? It's a negative 2 trough. 1, 2. There we go. So at this point in time, it shifted over the front of the wave front. Oh yeah, it just hit the center point there. So at time equals 1 second, wave B is just about to hit wave A. 1, 2, 3, 4. There we go. You see that? There's wave B. And that time equals 2 seconds, wave B shifted over 2 squares. There we go. Yeah? Like so. Do you guys see that? Am I doing that right? I think so. I'm just trying to make sure I lined it up there. Yeah? There we go. And then at 3 seconds, there we go. Wave B moves over another 2 feet. So 1, 2. There we go. 1, 2, 3, 4. Woo! And then finally, after 4 seconds, wave B moves another 2 feet, or 8 feet altogether. So the front of the wave should be there. So all I'm doing is just drawing each wave every second, traveling at 2 feet per second. There's wave B going to the left, and then wave A was going to the right. Next, what was the point of that? To annoy you, to draw little squares. No, we're trying to understand what happens in real life when waves interfere. In the green. Now we're going to apply the principle of superposition, which simply states that the resultant wave, when more than one wave interferes with each other, is a sum of each wave's amplitude at each point. Big fancy word for waves just add up. So you tell me, when do the waves start to add up? At what? 2 seconds, right? So notice we're going to go left to right. Here, wave A is at positive 2. What's wave B? Negative 2. So you know what happened? These waves just what? Cancel out. That's weird. And then at 3 seconds, they already passed through each other. 4 seconds. You know what? We're actually done. You see that? So in this case, the resulting wave cancels out at exactly 2 seconds. Later on, they might not exactly cancel out. Like here, number 4, Actually, this got numbered funny. 1, 2, 3, 4. The third situation over here, okay, I think the numbers just got shifted when I printed this out. Wave B is a little bit smaller. It's not going to quite cancel out. It's going to have a little blip. You can use the computer simulation to help you see it.